Welcome friends, this is my fourth video on differentiation for the class 12 students of Science and Arts of Maharashtra State Board. We solved some examples on chain rule last time. Actually we stated and proved the chain rule first and then we solved examples. At that time we solved those examples by using some substitutions for certain functions. We used sometimes u or v, etc. This time we shall solve the examples on differentiation of composite function by using chain rule, but we shall use slightly different technique. Means that is a direct method we call that as. We shall solve some examples using that direct method, and hereafter we shall use the same direct method for solving a few examples, and even we shall use that same method for solving the examples in the future. We shall take one example to understand that method. Tan of 2 raised to x. We want to differentiate tan of 2 raised to x with respect to x. So let us start the answer. Let y is equal to tan of 2 raised to x. Now we have to differentiate this with respect to x. Earlier we used to say tan of 2 raised to x is a function of 2 raised to x. Then 2 raised to x is a function of x. So we used to take this as u, this as y of course there, and then we used to get du by dx, dy by du and multiply them and use chain rule as dy by dx is equal to dy by du into du by dx, and we used to get the answer. So that is first method. Now here what we shall do different, see, we shall not bother about those u's and v's. We shall here directly write differentiating with respect to x, and think about this function. So dy by dx is equal to d by dx of y. Y is tan of 2 raised to x. So what I have done here is just nominal step. Y is tan of 2 raised to x. I wrote differentiating with respect to x. So differentiating means d by dx of y, left side d by dx of y, right side d by dx of whatever right side we had, tan of 2 raised to x. So now differentiating tan of 2 raised to x with respect to x means, see, you must know this, tan of 2 raised to x is a function which is found by using the functions tan x and 2 raised to x. This is a composite function of tan x and 2 raised to x. So basically tan of 2 raised to x looks like tan x, which is a standard function. Tan of 2 raised to x looks like standard function tan x, whose derivative, you must know, derivative of tan x is sec square x. So like we write derivative of tan x is sec square x, in the same manner derivative of tan of 2 raised to x, derivative of tan of 2 raised to x will be sec square 2 raised to x into, then multiply it by d by dx of replacement of x when you compare tan x and tan 2 raised to x. So replacement of x in this comparison is 2 raised to x. Tan x, tan 2 raised to x. What is x replaced by? 2 raised to x. So multiply this sec square 2 raised to x by d by dx of replacement of x, which is d by dx of 2 raised to x. Then you continue the simplification, sec square 2 raised to x as it is, and then d by dx of 2 raised to x. Now 2 raised to x is a standard function which falls in the category a raised to x, which is exponential function, and whose derivative is known to you. A raised to x, derivative for a raised to x is a raised to x log a. So derivative of 2 raised to x is 2 raised to x log 2. So it will be directly written as 2 raised to x into log 2. This is it. Earlier we used to write this answer. There we used to write this as dy by du, and this was du by dx. Then they were multiplied to get dy by dx. But here we have not bothered about taking u's and then multiplying dy by du and du by dx. We found this directly. You have to understand this technique, and for that we have to see some more examples. Let's see some more examples. See this new example. Differentiate with respect to x log of sine x. Again, it's a composite function. Log of sine x is a composite function because it is a composite function of log x and sine x. So we have to use chain rule. For that, we have to compare this with a standard function looking like log of sine x. Log of sine x looks like, isn't it? Log of sine x looks like log x, whose derivative you must know. Derivative of this log x is 1 upon x. So derivative of log of sine x should be 1 upon sine x in the first part. After that, we have to multiply it by d by dx of replacement of x while comparison is done. So when you compare these two functions, x is replaced by sine x. So remember these two or three things while answering. So let us see the answer. We have to differentiate log of sine x with respect to x. So what we do normally is we take y is equal to log of sine x. Then our work starts. We write normally differentiating with respect to x and then proceed. So left side with respect to x, if you differentiate, you will get dy by dx is equal to d by dx of left side is done, d by dx of right side, d by dx of right side is log of sine of x. Now like we discussed earlier, log of sine of x looks like log of x, and log of x's derivative is 1 upon x. So derivative of log x is 1 upon x, so derivative of log of sine x in that way will be 1 upon sine x. But that's not all. In chain rule we have to multiply at first part by d by dx of replacement of x when you compare the two functions. This log of x was compared with log of sine x. So what was x replaced by? X was replaced by sine x. So d by dx of that replacement, that is d by dx of replacement of x, d by dx of sine x. Now after that I have to write this first part as it is, 1 upon sine x into d by dx of sine x is something which you know easily. Sine x is the standard function whose derivative is directly known. So derivative of sine x is cos of x. Then multiply these two and you get cos x upon sine x, or you can directly write it as cot x. So in this manner we can answer differentiation of log of sine x. What we did is, log of sine x is not a standard function, it's a composite function. So we have to use chain rule, but we are using direct method now. So what do? Log of sine x is compared with the similar standard function log x, whose derivative is known to you, 1 upon x. That is the rough work. This is something which you have to do in rough. So compare that given function with the standard function. Then its derivative should be remembered. Log x is derivative 1 upon x. So derivative of log of sine x is 1 upon sine x. And into then d by dx of replacement of x when you compare the two functions. Replacement of x was sine x. So we wrote d by dx of sine x, which is cos x. And then we finished it as cot x. Let's see a new example. Differentiate with respect to x log of tan of root x. Log of tan of root x. So y we have to use as log of tan of root x. That's the nominal step. We have to use the some later we use y for denoting the given function. Y is equal to log of tan of root x. Then differentiating with respect to x, we get d by dx of left side, that is dy by dx, is equal to d by dx of right side, which is d by dx of log of tan of root x. D by dx of log of tan of root x. Now the real work starts. Here we shall compare this function, as this is not a standard function. Log x is a standard function, tan x is a standard function. Log of tan of root x is not a standard function. Log of tan of root x is the function of tan of root x. Tan of root x is a function of root x, and root x then is a function of x. So this is a composite function, so we need chain rule. But as you know, we are using direct method of solving examples on chain rule. So what we do is we compare log of tan of root x with the standard function similar to this. Log of tan of root x looks like log of x, isn't it? Log of tan of root x looks like log of x, whose derivative is 1 upon x. Directly we know that. So derivative of log of tan of root x will be similar to this. Log of x is derivative 1 upon x. So log of tan of root x, its derivative should be 1 upon tan of root x. So our first answer is 1 upon tan of root x. First part of the answer, 1 upon tan of root x, and then multiplied by d by dx of what was the replacement of x when we compared the two functions, log of tan of root x compared with log x, and we know it's x replaced by tan of root x. So replacement of x's derivative is d by dx of tan of root x. Now the first step is over. 1 upon tan root x, which you can write cot root x also if you want, then d by dx of tan of root x. So first part repeated, 1 upon tan of root x, then d by dx of tan of root x. Now again, tan of root x is not a standard function. Tan of root x is a function of root x. In root x there is a function of x. So again we need chain rule. And if you need chain rule, what you do is compare that tan of root x with the standard function. Which standard function it looks like? Tan of root x looks like tan of x, whose derivative is tan of x's derivative is sec square x. So derivative of tan x is sec square x. So derivative of tan root x will be sec square root x. So in the first part I would write sec square root x. That's the derivative of tan root x in the beginning, and then into d by dx of replacement of x. When you compare tan x and tan root x, what was x replaced by? X was replaced by root x. So d by dx of root x. Now we have to repeat this part up to this because there is no differentiation required in this part. So it's 1 upon tan root x into sec square root x. I can collectively write them as sec square root x upon tan root x, and then into d by dx of root x. Now root x, look at the function root x. Root x is the standard function. Root x is a function of x only. So if it is a standard function, its derivative is directly known. Root x is derivative, we know it's 1 upon 2 root of x. So derivative of y is equal to log of tan root x is sec square root x divided by tan root x into 1 upon 2 root x. And this is a rough work, so you can just get rid of that as soon as possible. Once you understand the comparison, this is not required. In this manner, we can get this answer of differentiation of log of tan of root x. Let us start with the first example from exercise 1.1. Differentiate with respect to x 4x cube minus 3x square plus 5x minus 4 bracket raised to 4. Now as usual, we take this function as y. So let y is equal to 4x cube minus 3x square plus 5x minus 4 bracket raised to 4. Now we shall differentiate this with respect to x. So we write derivative of y with respect to x means dy by dx, which is equal to d by dx of this whole right side, 4x cube minus 3x square plus 5x minus 4 raised to 4. So what we have to do is we have to differentiate this 4x cube etc. raised to 4 with respect to x. So d by dx of this is to be found. Now this is not a standard function, so you have to compare this function with a standard function similar to this. Now which function is similar to this function? this bracket contains some expression. This bracket raised to 4, it looks like simply x raised to 4, which is a standard function. Now its derivative should be known to us. X raised to 4, its derivative is 4x cube. So 4x cube is the derivative of x raised to 4. So what we have is some bracket raised to 4. So its derivative should be 4 into that bracket raised to 3 into d by dx of that replacement of x. So what is this bracket containing? 4x cube minus 3x square plus 5x. Just repeat this expression. So just like x raised to 4's derivative is 4x cube, derivative of d by dx of this bracket raised to 4 is 4 into this bracket cube in the initial part into d by dx of replacement of x. When you compare x raised to 4 and this bracket raised to 4, what was x replaced by? X was replaced by this expression in the bracket. So d by dx of replacement of x, which is d by dx of 4x cube minus 3x square plus 5x minus 4. So we shall repeat this first part as it is. You can keep this up to this the same. After this you can write it properly. I'm just leaving and going forward. This is the most important part. This is d by dx of 4x cube minus 3x square plus 5x minus 4. How do you differentiate this? It's a polynomial and its derivative is easily found. It's 4 into x cube, so constant written in the beginning 4, then derivative of x cube is written, it's 3x square minus 3x square's derivative, 3 is a constant written in the beginning, and then derivative of x square is 2x, then plus 5x, 5 is a constant into function. If you want to differentiate constant into a function, take that constant out of the differentiation and then write the derivative of the function. So 5 taken in the beginning, constant outside, then derivative of x is 1 and minus 4, 4 is a constant only, so its derivative is 0. So you can write this if you have not written. It's just the same thing which is written in the previous. See this new example. Differentiate with respect to x, square root of x square plus another square root here, x square plus 1, square root of x square plus root of x square plus 1. So as usual we consider this function as y and find dy by dx. So we have to differentiate with respect to x. I get dy by dx on left side, and on right side d by dx of, what is the right side? It is d by dx of root of x square plus, just I have to write the same thing here. Now in this step, in the next step we have to differentiate this with respect to x. So root of x square plus root of x square plus 1, again it's not a standard function, composite function, it's a composite function, so we have to use chain rule. So we have to compare this function with the suitable standard function. Square root of anything looks like square root of x. So square root of x it looks like, so comparison is done and the replacement is understood. The replacement of x in this case is this, everything inside the root. So square root of x square plus square root of x square plus 1 is compared with square root x, whose derivative is known to us. Its derivative of root x is 1 upon 2 root of x, that we know. So derivative of root x is 1 upon 2 root x. Derivative of root of x square plus root of x square plus 1 should be 1 upon 2 root of whatever it contains. It contains x square plus square root of x square plus 1, and then multiply this by d by dx of replacement of x. When you compare root x and root of x square plus root of x square plus 1, x was replaced by this highlighted part, which is x square plus square root of x square plus 1. Now we have to just repeat this part and think about this part. So this part is repeated 1 upon 2 root of x square plus square root of x square plus 1 as it is. Then what about this? D by dx of x square plus root of x square plus 1. Now this is u plus v. So derivative of u, derivative of x square, 2x. You can directly write that 2x. This is standard function. So directly derivative is written. Now derivative of this, derivative of x square is written plus derivative of root of x square plus 1. Here this is not a standard function. Root of x square plus 1 is a function of x square plus 1. And x square plus 1 is then the function of x. So I have to compare this with the standard function. Again, root of x square plus 1 compared with the same standard function root x, whose derivative is 1 upon 2 root x. So derivative of root x is 1 upon 2 root x. So derivative of root of x square plus 1 should be 1 upon 2 root of x square plus 1 in the beginning, and then into d by dx of replacement. When you compare these two functions, what was x replaced by? X was replaced by this x square plus 1. So x was replaced by x square plus 1 when you compare these two. So derivative of replacement means derivative of what? Derivative of x square plus 1, and then the bracket will complete. So this part is just multiplied to this. This is separate. X square's derivative 2x is written separately, and this is derivative of this part. Now I shall continue with calculations here. Derivative of only thing we have to find in the next step. This is repeated. This will also be repeated, and this has to be found out. Derivative of x square plus 1 will be derivative of x square plus derivative of 1. U plus v rule. Derivative of x square is 2x, and derivative of 1 being a constant, derivative 0. So this matter is going to be what? This is going to be just 2x. Just replace this by 2x and finish this answer. You can simplify it a little bit, because this 2 and 2 can be cancelled. So we shall do it in the next step here. So continue this step there. Dy by dx is equal to 1 upon 2 root of x square plus square root of x square plus 1 into, this is repeated there, into this bracket. Now this 2x is no change there, plus 1 upon 2 root of x square plus 1, and then this derivative you calculated, x square derivative 2x plus 1's derivative 0, so it is just 2x. Just 2x. Can you see this? This is 2x. I can write this 2x here also. 2x. Then you can simplify this by just cancelling this 2 and this 2, and write this almost in the end now. 2 root of x square plus root of x square plus 1 into bracket 2x plus x upon root of x square plus 1. That's it. This is dy by dx. We started with this example, took it as y, then root of something, root of x square plus root of x square plus 1. It looks like root of x. So derivative of root of x square plus root of x square plus 1 was found as 1 upon 2 root of that matter into d by dx of the quantity inside the root. Then this was repeated and this was found out. Derivative of x square was 2x. Derivative of root of x square plus 1, again we needed chain rule there. Root of x square plus 1 was compared with root of x, and then that root of x's derivative is 1 upon 2 root of x's derivative is 1 upon 2 root x. So this derivative is going to be 1 upon 2 root of x square plus 1 into d by dx of replacement x square plus 1. Then we found derivative of x square plus 1 as just 2x, that I mentioned in rough here. We can finish it off in this manner, 2 to cancelling, and you get this as the final answer. See this new example. Differentiate with respect to x. cos square log of x square plus 7. So we normally take it as y. So y is equal to cos square log of x square plus 7. Now we understand that cos square x means cos x whole bracket square, which is cos x into cos x, and cos x whole square can be written as cos x into cos x also. These are all same things. So cos square x is cos x whole square. So we shall write this as cos of log of x square plus 7 whole bracket square. So we can understand this function easily. This and this is the same. So we haven't started differentiating yet. We have just written y in a simpler manner. Now we can compare this with a standard function. Which function it looks like? Some bracket raised to 2. It looks like x square. So derivative of x square. This is x square looking like x square, whose derivative should be known to you. Derivative of x square is 2x. So derivative of this function is going to be differentiating with respect to x. Of course, we have to mention it here. Differentiating with respect to x, you will get dy by dx is equal to, now like I said, we compare this bracket square with x square. So derivative of x square is 2x. Derivative of this bracket square will be 2 into that bracket. 2 into that bracket. Cos of log of x square plus 7, and after that we have to multiply this by d by dx of replacement of x. When you compare these two, what is x replaced by? You compare this bracket square with x square. So x is replaced by this cos of log of, see this comparison, x square and this bracket square. So x is replaced by this bracket. So what is that bracket containing? It is cos of log of x square plus 7. So in the next step we shall repeat this part and just focus here. I have to find derivative of that second part. So 2 into, this is the repeated part, 2 into cos of log of x square plus 7 into, then here you have to consider this function cos of log of x square plus 1. Which function it is looking like? Cos of log of x square plus 1 is not a standard function. It is a composite function. So we have to compare this with standard function. Which function? Cos of anything looks like cos of x, and cos of x, if you differentiate, you get minus sine of x. So derivative of cos of x is minus sine x. So derivative of cos of log of x square plus 1 is minus sine of log of x square plus 1 into d by dx of replacement of x. When you compare this cos of x with cos of log of x square plus 1, what is x replaced by? X is replaced by log of x square plus 1. So it will be d by dx of log of x square plus, it's not 1, x square plus 7. So this is 2 cos of log of x square plus 7 as usual. Then minus sine, this is coming from this derivative. Derivative of cos of x is minus sine x. So derivative of cos of log of x square plus 1 is minus sine of log of x square plus 7, and into d by dx of replacement of x. When you compare these two, x was replaced by log of x square plus 7. So in the next step we shall repeat this whole part up to this, and just d by dx of something is asked. That has to be found out. So I shall repeat this step, and I write this as 2 into cos of log of x square plus 7 into minus, this minus sign can be written in the beginning also. So I can write in the beginning, it's minus 2 cos of log of something into sine of log of x square plus 7 and then into this, now this part d by dx of log of x square plus 7. Again, log of x square plus 7 is not a standard function. Log of x square plus 7 looks like log of x. So log of x, it is looking like log of x, and whose derivative we know is 1 upon x. So log of x and log of x square plus 7, these two are compared. Log of x's derivative is 1 upon x. So log of x square plus 7's derivative will be 1 upon x square plus 7 to begin with, and into d by dx of replacement. You compared log of x square plus 7 with log of x. What is x replaced by? X was replaced by x square plus 7. So d by dx of x square plus 7. So you have almost completed this answer, this 2 etc. This whole part will be repeated up to this, and then see this d by dx. Just have to find this derivative, d by dx of x square plus 7, and d by dx of x square plus 7, you need u plus v rule. Derivative of u plus derivative of v. Derivative of x square is 2x and derivative of 7 is 0. So derivative of x square plus derivative of 7 will give you 2x plus 0. Means this will be just 2x. In the next step, you can write this whole matter as 2x and then finish this. So we shall write the whole answer here. dy by dx equal to, so writing this part in this step here as it is, and then 1 upon, up to this it is the same, then 1 upon x square plus 7, that also is same. Then d by dx of x square plus 7 is d by dx of x square plus d by dx of 7, which is d by dx of x square is 2x plus d by dx of 7 is constant, so derivative is 0, so not written there. So we can finish this by writing this 2x here and upon x square plus 7. And even there is one interesting expression or one formula there which you can use here. See, 2 sine theta cos theta, you know this formula, it is 2 sine theta cos theta is equal to sine 2 theta. So we can use this formula and write this as, this is 2 sine theta into cos theta, the same theta is there. So I can write this as minus as it is sine 2 theta, means sine 2 into what is our theta? This is our theta. See this, 2 sine theta cos theta, it is sine 2 theta, that becomes sine 2 into this theta, which is log of x square plus 7. So sine of 2 theta written here, minus sign repeated here. So this much part is already written. So what remains after that is just 2x upon x square plus 7. You can arrange it in a better manner. You can write that 2x in the beginning and whole divided by x square plus 7 also. So it's minus 2x sine of 2 log of x square plus 7 and then whole divided by x square plus 7. So that way we can write dy by dx in the final form. Now see this new example. Differentiate with respect to x, log of x to the base e square. So we shall take this as y initially. Let y is equal to whatever example they have given, log x to the base e square. Now here we need some simplification before we differentiate. So what simplification is applicable here? Log of a to the base b. You know this rule of logarithm, log of a to the base b can be written as log a divided by log b to the same base you choose. Say I have chosen k, or even I can choose e also in both cases, or it's not mentioned means it is understood to be e. So log a to the base b can be written as log a upon log b. So here also we can use this rule and write y as log of log x divided by log of e square. When I don't write any base here, I understand that it is e. which can be still simplified as log of log x, that's no change there, and then log of e square no is log of x raised to n is n log x, log of x raised to n is n log x. So you can write log of e square as 2 log e, 2 log e. Again, log e with base e, not mentioned with base e, is 1. Log e is 1. So you can write this as just 1, and this will be log of log x upon 2 into 1, that means just 2. So 2 into 1, that is 2, which can be written in the better way as 1 by 2 into log of x. So this is the y in the simplest form. We can differentiate after this. So no differentiation is done here. You can see those different laws of logarithms which are applied here, which are used here, and the given function is simplified a little bit. And now we can differentiate this, and let us see what is the derivative here. So now in the next step I shall write differentiating with respect to x. Differentiating with respect to x. So what is our y? What is our y? Y is half log of log x. So dy by dx is equal to d by dx of half log of log x. I know this function is differentiated by taking this constant out of the derivative first, because derivative of constant into function then is equal to constant outside and derivative of that the remainder of the function. So 1 by 2 being a constant comes out into d by dx of log of x, which is further simplified as half as it is. Then d by dx of log x. Now this is the standard, this is the composite function. Log of log x is not a standard one, it's a composite function. So it has to be compared with the standard function. Which function it looks like? Log of log x. Log of anything looks like log of x. Log of log x looks like log of x, whose derivative is 1 upon x. So derivative of log x will be just like derivative of log of x is 1 upon x. Derivative of log x will be 1 upon log x into then d by dx of replacement of x. When you compared log of x and log of log x, what was x replaced by? X was replaced by log x. So d by dx of replacement of x, that means d by dx of log x. Now what is left is just this part. This will be repeated. 1 upon 2 log x is the repeated part into d by dx of log x. Now this is not a composite function, it's a standard function. Its derivative is directly known. Log of x, its derivative is 1 upon x. So I need not write it in the chain form. It's directly written as 1 upon x. So you can finish this as 1 upon 2x log x. So dy by dx is equal to 1 upon 2x. Just go through these steps. You initially had this function log of x, log of log x to the base e square. What did we do? We used the laws of logarithm and wrote this in a simplified form like this. And then after this we differentiated it. Differentiation starts by taking this constant outside the derivatives, and then the remaining part is differentiated. Then this differentiation of log x is done by comparing log of log x with log of x, whose derivative is 1 upon x. So derivative of log x is 1 upon log x into d by dx of replacement of x, which is d by dx of log x, which is directly written, and then it is finished in a nice form. See this new example. Differentiate with respect to x tan x degree. So we take the given function as y is equal to tan x degree. Then differentiating. Now before differentiation we have to think about this function a little bit closely. Tan x degree, it's not tan x. When you write just tan x, you know that its derivative is sec square x. when you remember this derivative of tan x as x square x, it's actually x radians, which is not mentioned. So whenever tan x is written, you have to understand that it is tan x radians. Now what is given here is tan x degree. So derivative of tan x degree is not sec square x degree. Sec square x degree. This is not the answer for this derivative. Tan x, its derivative is sec square x, but x is in radians. It's not mentioned. We have to understand it is in radians. So what happens when you have degree unit used for x? So what we do is we convert this given degree angle into radian, and for conversion of a degree angle into radian, what do? We multiply degree angle by pi by 180. Multiply degree angle by pi by 180 and get radian angle. So what we shall do here, we write tan x degree is multiplied by pi by 180. Now it is radians. So radian need not be written. I shall write in one step. Next step I shall just write tan of x pi by 180 means pi x by 180, and radian need not be mentioned. Now this is our y in the better form. Now we shall differentiate this. Now the differentiation of tan of anything will be done by comparing this function with tan of x, whose derivative is sec square x. So derivative of tan x is sec square x. So derivative of tan of any bracket is sec square of that bracket. That means now after differentiation, of course, is mentioned. Differentiating with respect to x, we have to mention this, and then the next step starts. Dy by dx is equal to derivative of this is sec square. Instead of x we have pi x by 180, and then into d by dx of, whenever the comparison is done, you have to understand what is the replacement of x. Replacement of x is pi x by 180. So d by dx of pi x by 180. Now I have to repeat this sec square pi x by 180. It's in radians. So we can get back to sec square x degree also, because we don't have to differentiate this any further. So I can write it sec square x degree also. What you have to simplify is this part. This is already solved. So no need of writing this in this complicated form. I may write it in sec square x, write this as sec square x degree, or I can leave it like this only. So I will choose this way. Then d by dx of pi x by 180. Now what is this d by dx of pi x? It looks a little bit complicated example or expression, but what does it mean? It's just simple one, mx, constant into x, just like 3x, pi x. How do you write the derivatives? You take this constant out, means 3 is written out, and derivative of x is 1. So 3 into 1 is 3, answer is 3. So derivative of mx is m, derivative of phi x is phi. In the same manner, this is pi by 180 is a constant, just like that, m into x. So derivative of constant into x, constant is written outside, pi by 180, and derivative of x is 1. So this is just how much? This sec square x degree into pi by 180. So we can leave it as it is. This is the answer for this kind of question. Sec tan x degree was differentiated. Even you can think about sec x degree. Sec x degree will be written as sec x into pi by 180 into tan degree. That is converted into radians first, and then its derivative is remembered. Sec x's derivative is sec x tan x. So it will be sec pi x by 180 into tan pi x by 180 into d by dx of pi x by 180, which is pi by 180. Then think about tan x degree, cot x degree. They can be rearranged in first of all radians and then differentiated. So this is how we can find derivative of trigonometric functions with degree angles. So today we solved some examples on chain rule from exercise 1.1. I took the examples from question number 1 and 2. There are 2 or 3 more questions in this exercise. And also there are a few examples left in question number 1 and 2 also. You can do them at home. So practice this kind of examples, and in the next video we shall see the remaining examples, remaining questions from the exercise 1.1. Keep practicing, and if you have any difficulties you can make those comments in the comment box, and I can try to solve them.